In this video, I'm going to show you how to calculate or predict the concentrations of reactants in products when equilibrium is established. Last class, I introduced this idea of equilibrium, and in that lesson, we did an example involving percent reaction. So we were looking at hydrogen and iodine coming together to form 2 moles of hydrogen iodide, and we had 3 different trials that had differing amounts of reactants, and we were noticing that the concentrations of products and reactants when equilibrium was established was a lot different than what we expected based on our stoichiometric calculations. And so the purpose of today's lesson is to show you how you can actually predict what these specific values will be when equilibrium is established. There's a number of different ways of solving this particular problem, and we're going to look at those different methods over the next few classes. So we'll start off by looking at this fictitious reaction involving 1 mole of X reacting with 2 moles of Y to form 3 moles of Z. So if this was a grade 11 problem, and I presented you with 1 mole of X, assuming that there was a sufficient amount of Y, then we could expect there to be 3 moles of Z produced. Alternatively, another grade 11 problem would be if I gave you, let's say, 4 moles of Y, how much X would you need? Well, based on, again, that ratio between X and Y, you would expect 2 moles of X to be consumed along with those 4 moles of Y. Now, the problem with these types of grade 11 stoichiometric problems is that, again, you're assuming that the reaction only goes in one direction and that you have a percent reaction of 100%, that the reaction proceeds to completion. But with our understanding of collision theory, we now know that that products have the capacity to react with themselves and revert back to reactants. So how can you predict, then, the amount of product and reactants that you should expect at equilibrium? So to answer those types of problems, it's handy to look at the products and reactants under 3 different categories. Their initial concentrations, the change in their concentrations, as well as their equilibrium concentrations. And we usually put all of this information into a table, and these types of tables are often referred to as ICE tables. So just to further clarify what I mean by initial change in equilibrium, initial refers to the initial concentrations of reactants and products before the reaction begins. Just skipping a little bit here, equilibrium refers to the concentrations of reactants and products when equilibrium is established, which means that change refers to the change in concentrations of those reactants and products from when the reaction started up until the point when equilibrium is achieved. Now, one thing that I'd like to highlight here is that every time I talk about initial change in equilibrium, I'm talking about concentrations. So whenever you're using an ICE table, you need to make sure that the values that you put inside that ICE table are in molar concentrations, are in moles per liter. Let's take a look at an example here. We're going to start off with hydrogen and fluorine reacting to form 2 moles of hydrogen fluoride. And we're told that the reaction begins with 1 mole per liter of hydrogen and fluorine gas and no hydrogen fluoride to begin with. And the question is asking us to calculate or to predict the concentrations of hydrogen gas and hydrogen fluoride at equilibrium if the equilibrium of concentration of fluorine gas is measured to be 0.24 moles per liter. So again, we're told the initial concentrations of our reactants and products, as well, we're also provided with the equilibrium concentrations of one of the reactants, fluorine gas. So I'm going to show you how to use an ICE table. There are 3 steps that you need to complete when you're using an ICE table. And so for the sake of just introducing you to this ICE table, I've created a brand new ICE table for each individual step. When you are trying these ICE tables on your own for homework or on a test situation, you'd only need to make one single ICE table. I'm just making 3 for just for this one specific example. Okay, so when we start off with our ICE table, the very first row will be our balanced chemical equation, and I dedicate a column for every reactant and product. So I've got a column here for hydrogen. Pardon me. I've got a column here for hydrogen, I've got a column here for fluorine, and then I've got a column here for hydrogen fluoride. As well, I have a row for my initial concentration, I've got a row here for my change in concentration, and I've got a row for my equilibrium concentration. And as well, when you're creating your own ICE tables, using the acronym I, C, and E is sufficient. There's no need to write out initial concentration, change in concentration, and so forth there. Okay. Now I'm just going to skip over this text for a second. I'll come back to it. So the very first thing I'm going to input here is the initial concentrations, which were provided in the question. So we were told that we have 1 mole per liter of hydrogen. We were told that we have 1 mole per liter of fluorine. As well, no product was present to begin with. Now, even though the reaction will not proceed to completion, that the percent reaction will not be 100%, stoichiometric ratios will still be observed. So, in other words, hypothetically, let's just say only 0.5 moles per liter of hydrogen was consumed. The same amount of fluorine would also be consumed because the ratio is 1 to 1. So, if 0.5 moles of hydrogen gas, don't write this down, by the way, if 0.5 moles per liter of hydrogen gas was consumed, then I would also expect 0.5 moles per liter of fluorine gas to be consumed. And because the amount of the ratio between reactants and products is 1 to 2, I would then expect 1 mole per liter of hydrogen fluoride to be produced as a result. So stoichiometric ratios are always observed. The problem is we just don't know how much of that reactant is going to be consumed. That's the problem that we're trying to solve here. So for now, what we're going to do is we're going to let X represent the change in concentrations of reactants and our products. Furthermore, we're also going to allow the coefficient of X to be equal to the coefficients in the balanced equation. So for now, so in my change column here, now I'm going to reveal a little bit too much. So right now, I'm going to put an X for my reactants as well as my products. As well, the coefficient of X will be the same as the coefficients from the balanced chemical equation. So the coefficient of X for hydrogen is 1, the coefficient for fluorine is 1, and the coefficient for hydrogen fluoride is 2. So then how do I come up with the negatives and positives then? For now, we're going to assume that because we have nothing but reactants to start off with and no products, it would make sense that the reaction will proceed by moving in the forward direction to begin with. And so that means that our reactants are going to be consumed, or in other words, the reactants are going to decrease in concentration, and that means our products are going to increase in concentration. So in other words, I'm going to put a negative sign for my reactants and a positive sign for my products. So again, just to put that all together one more time there, for my row for change, I'm going to put an X for all my reactants and products. The coefficients for X will be the same as the coefficients from the balanced equation. Reactants will be given a negative sign. The products will be given a positive sign. Okay? And then finally, the equilibrium row. All you'll do there is just add these two together. So it'll be 1 plus negative X, which can just simplify to become 1 minus X. So that'll be the same thing here. 0 plus 2X is just 2X. So that is a generic expression that we have for the equilibrium concentrations of everything. But now it's time to actually figure what the specific values are. And this is where the provided value of the equilibrium concentration of fluorine gas comes into play here. We know what the concentration of fluorine gas at equilibrium is. We know it's 0.24. So I know that this value here is equal to 0.24. So with that information, I can use that to help me solve for X. And so knowing that 1 minus X is equal to 0.24, I can use some algebra here to solve for X. That X does not represent the equilibrium concentrations. If if you remember, in my ICE table, just to scroll back up a bit here, I had hydrogen gas's equilibrium concentration as being 1 minus x, and hydrogen fluoride as being 2x. So now that I know what x is, I can use that to solve for the equilibrium concentrations, which is what I'm doing here. So 1 minus x, or 1 minus 0.76, becomes 0.24, and there's no surprise there that the concentration of hydrogen ends up being the same as the concentration of fluorine gas at equilibrium. And the concentration of hydrogen fluoride is 2x, or 1.52 moles per liter. Now you may think that, well, the ratio between hydrogen and hydrogen fluoride was 1 to 2. So if it's 0.24 here, shouldn't my concentration of hydrogen fluoride then be 0.48? And you have to realize that this value of 0.24 represents the amount of hydrogen gas that's left over. In fact, if you start off with 1 mole per liter and 0.24 moles per liter is left over, that means that 0.76 moles per liter of hydrogen was actually consumed, and twice as much of hydrogen fluoride will be produced as a result. So hopefully that's a lot of red ink on that page there, but I hope that makes sense. All right, let's take a look at one last example. I'll do so in the second part here. Okay, in our second part of calculating concentration at equilibrium, we're going to look at ammonia being decomposed into nitrogen and hydrogen gas. Now, although this is a very exciting reaction, there's no need for there to be a forte sign. I'm not too sure why Microsoft Word thinks that my chemistry is very musical. As much as I would love there to be more music in chemistry, we've got to have that as 2 single-headed arrows pointing in opposite direction. All right, so we're going to start off with 4 moles of 4 moles of ammonia introduced into a 2-liter container, heated up to a particular temperature, and then at equilibrium, the amount of ammonia at equilibrium happens to be 2 moles. So we're now asked to figure out the equilibrium concentrations of everything else. So again, we're told that we have a 2-liter container. We have 4 moles of ammonia to begin with, 2 moles of ammonia at equilibrium. Now, as I mentioned earlier, when you're using an ICE table, all the values that are provided have to be in moles per liter. So the very first thing I'm going to do here is convert my quantities into molar concentrations. So again, that molar concentration is moles per liter. So I'm going to take my 4 moles divided by the 2 liter to give me 2 moles per liter as my initial concentration. And my equilibrium concentration of ammonia was 2 moles in a 2-liter container. So that molar concentration ends up being 1 mole per liter. So I'm going to create an ICE table. That first row will be my balanced chemical equation. I'll devote a column for each reactant and product. My initial concentrations, all I had was ammonia. Although it wasn't mentioned explicitly, it's implied that there was no product to begin with. For my change, again, I'm going to put an X for everyone, an X for my reactant and my 2 products. The coefficient of X will be equal to the coefficients from the balanced equation. So there's a 1 here, so that's why there's a 1 there. A 3 for hydrogen, which is why there's a 3 there. As well, reactants will have a negative sign, products will have a positive sign, simply due to the fact that as this reaction proceeds, reactants will be used up and products will be produced. For the equilibrium row, you just add the initial and the change together. And so I have 2 minus 2x, 0 plus x is x, 0 plus 3x is just 3x. Now the last bit of information is that the equilibrium concentration of ammonia was provided. We were told that the quantity of ammonia at equilibrium was 1 mole per liter. So I'm going to take the 2 minus 2x, set it equal to 1 mole per liter, allowing me to solve for x. And that's what I'm doing here. So x ends up being 0.5 moles per liter. So that means that nitrogen, because nitrogen is equal to x, its concentration will be 0.5 moles per liter. Hydrogen will be 3 times 0.5 moles per liter, which works out to be 1.5 moles per liter. And that's the equilibrium concentrations of my two products, which is what the question was asking for. Super. So that's all there is. We have a worksheet. If I can see if here it is there. So there are 4 questions. Three questions. This last one's a tricky one. I think I've got a typo here. I think there needs to be a subscript there of 2. Whoops. All right, that's proving to be. There we go. And I don't know why my word is having difficulty with the double-headed arrows, but insert the double-headed arrows where you see these boxes, please. So give those a shot. We'll take them up not for Friday, but for Thursday of next week. Friday will be a day to prepare for a Chapter 6 test. Tuesday will be the Chapter 6 test, and then Thursday we will take the opportunity to take up these questions. As well, Thursday of next week is the Grade 12 University of Waterloo Chemistry Contest. Not a lot of you registered, but some of you did. It will be in our classroom starting at 8:45. So please show up. If you did not register and are really regretting that decision, or just can't sleep because you wish you signed up for the chemistry contest, then just show up. We'll make it happen. All right. Thank you so much. I'll see you guys on Friday.